This video is for Chemistry in the Earth System, Unit 2.5, Periodic Trends. What other periodic trends besides reactivity occur, and how are they explained? Our first main idea, atomic radius, observed periodic trends. One measure of atomic size is the distance from the center of the nucleus to the outermost electrons. This distance is defined as the atomic radius. The size of the radius is hard to describe because the electron cloud does not have a well-defined surface. A common way to describe it is half the distance between the nuclei of neighboring atoms. These might be identical atoms that are bonded together, or atoms next to each other in a crystal. The atomic radius does not vary much for transition metals, but it does for main group or representative elements. The diagram on your screen here shows the changes. For main group elements, the atomic radius increases as you go down a group. This increase results because a new energy level is added as you move from one period down to the next. The outermost electrons occupy energy levels that are farther and farther from the nucleus with each shift to a new period. Again, look at this diagram to see what happens to the atomic radius of main group elements as you move from left to right within the same period. With each move to the right, one more proton and one more electron are added. You might think that the addition of these particles would result in the atom of larger size. However, the diagram here shows that for most main group elements, atomic radius decreases from left to right across a period. Something else besides a physical increase in number of subatomic particles affects the radius. What could explain this observation? Atomic size, the effect of nuclear charge. The decrease in atomic size across a period can be explained by the effect of increasing nuclear charge. As you move from left to right within a period, the numbers of protons and electrons increase. This increases the amount of positive charge in the nucleus. And since the electrons are being added to one energy level, they occupy the same region. And as a result, they are held more tightly by the increasing positive charge of the nucleus. Factors underlying periodic trends. The factors that explain the observed trends in chemical reactivity and atomic radius apply to other properties of the elements. Along with the chemical reactivity and atomic radius, the important factors are total number of electrons in the atom, the size of the nuclear charge, the distance between the nucleus and the outermost valence electrons, and the amount of shielding between the positively charged nucleus and the negatively charged electrons in the outermost energy level. All other periodic trends can be explained using these four factors. Periodic trends in ionic radius. An ion is a charged particle that results when an atom loses or gains electrons. The charge results from an imbalance in the numbers of protons and electrons present. Ionic radius is the distance from the center of the nucleus to the outermost electrons of an ion. The ionic radius, just like the atomic radius, is hard to describe because the electron cloud does not have a well-defined surface. Metal atoms become ions by losing electrons. In these ions, the net charge is positive because the protons outnumber electrons. These ions are smaller than their neutral atoms because there is more pull by the nucleus on the electrons in the outer energy level. Nonmetal atoms become ions by gaining electrons. The net charge is negative because now the electrons outnumber protons. These ions are larger than their neutral atoms because the pull of the nucleus on the electrons is weaker. Among metals and among nonmetals, ionic radii tend to decrease as you move left to right across a period. The nonmetal ions, however, tend to be larger than the metal ions. Periodic trends in metallic character. Metallic character is the measure of how easily an atom loses an electron. The diagram on the screen here summarizes the periodic trends in this property. Metallic character decreases across a period and increases down a group. The four factors noted earlier can explain these trends. The addition of new energy levels as you move down a group has two effects. The distance between the nucleus and the outermost electrons increases, and greater numbers of energy levels occupy this distance. The shielding effect, demonstrated on the screen here, of the inner electrons and the increasing distance reduce the effective nuclear charge experienced by the outermost electrons. As a result, less energy is needed to remove one outer electron, and so metallic character increases. Within a period, however, only the nuclear charge factor is at work. The number of protons increases as you move from left to right, but no new energy levels are introduced. Therefore, as you move from left to right, the outermost electrons experience a greater and greater positive charge from the nucleus, and it becomes more difficult for an electron to be removed. Therefore, metallic character decreases as a result. Periodic trends in ionization energy. Ionization energy is the energy needed to remove one electron from the outermost energy level of a gaseous neutral atom to form an ion having a +1 charge, like the sodium atom on your screen here. The energy required to remove the outermost electron from the gaseous +1 ion is called the second ionization energy. It is larger than the first ionization energy, and the third ionization energy is higher than the second. This is because fewer electrons remain to shield the nucleus from the electrons, and its pull is stronger on the remaining electrons. Thus, each successive electron removed from the atom feels an increasingly stronger effective nuclear charge. As we can see on this ionization energy chart, ionization energy decreases as you go down within a group and increases as you go from left to right across a period. Ionization energy behaves opposite to metallic character. In addition to new energy levels as you move down a group, there are two effects. The distance between the nucleus and the outermost electrons increases, and greater numbers of energy levels occupy this distance between them as well. That shielding effect of the inner electrons and the increasing distance reduce the effective nuclear charge experienced by the outermost electrons. Less energy is therefore required to remove an outer electron. This increases metallic character, but decreases ionization energy. Within a period, only the nuclear charge factor affects metallic character. The number of protons increases as you move from left to right, but no new energy levels are introduced. Therefore, as you move from left to right, the outermost electrons experience a greater positive charge from the nucleus. More energy is required to overcome this pull. Therefore, metallic character decreases, but ionization energy increases. Periodic trends in electronegativity. Electronegativity is defined as the tendency of an atom to attract electrons. The electronegativity chart on the screen here shows the periodic trends observed for this property. Electronegativity decreases as you go down within a group and increases from left to right across a period. Once again, the factors discussed earlier become important when explaining this trend. As you move down a group, the distance between the nucleus and the outermost electrons increases. Also, more energy levels filled with electrons shield the outermost electrons from the nucleus. Both factors decrease the effective nuclear charge experienced by those outermost electrons. This decreases the positive pull of the nucleus on the electrons, which decreases the element's electronegativity. Moving from left to right within a period, however, the atoms gain electrons and protons, but no new energy levels are added. Therefore, as you move from left to right, the outermost electrons are added to the same energy level. The added protons in the nucleus cause a greater positive charge, which pulls on the electrons. This increasing positive pull makes the elements more electronegative. At this point, you should be able to generate a full and appropriate response to today's essential question. What other periodic trends besides reactivity occur, and how are they explained?